Hi students, welcome back to Physics for All YouTube channel. In today's session, I am going to explain you about very important topic, that is extrinsic semiconductor. If you can understand about this extrinsic semiconductor, then the total chapter will be very easy. Please watch this presentation completely without skipping. Okay. Now, what is the meaning of extrinsic semiconductor? An impure semiconductor. An impure semiconductors are known as extrinsic semiconductor. Okay, when some impurities are added into the pure semiconductors, then it results the formation of extrinsic semiconductor. Before adding or before going to the topic of extrinsic semiconductor, now we have to understand about the important definition, that is doping. What is the meaning of doping? The process of addition of impurity atoms into pure atoms. The process is called as doping, and the element to be doped into the respective material, that elements are called as dopant. In general, the ratio of doping is equal to 1:10 power 8. In this 1:10 power 8, 1 represents impurity atom and 10 power 8 represents impurity. 10 power 8 represents pure atom. That means what you can understand, more number of pure atoms are there and less number of impure atoms are there. This is about the ratio of doping to make N-type or P-type, and this doping ratio can be changed depending on our requirement. That is important point we have to understand. Now coming to the very first one, depending on the type of impurity atom added into the pure semiconductor crystal, we can categorize into two types of extrinsic semiconductor. Number one is a N-type semiconductor and number two P-type semiconductor. Now let us discuss about the N-type and P-type in detail. The very first one is known as N-type semiconductor. Now how can we define N-type semiconductor? If a small amount of pentavalent impurity atoms are doped into the pure silicon or pure germanium or pure semiconductor crystal, such semiconductors are known as N-type semiconductor. Okay. Now to understand about the N-type semiconductor. First of all, I am going to consider silicon, intrinsic silicon I am going to consider. Now I am going to draw the silicon crystal. Now this is a one silicon crystal. Already in the last session I am explained about the nature of the silicon. So how many electrons are there in the case of silicon? Silicon is a tetravalent impurity. What is the meaning of tetravalent? Tetravalent means 4 electrons are in the outermost level. That is the meaning of tetravalent. So you can take one silicon crystal which contains large number of silicon atoms. So all are silicon only. So these are the silicon crystal. Before starting the entire semiconductor, first of all I am going to consider intrinsic silicon, which contains 4 valency electron. So 4 valency. So this is a 4 valency electron of each silicon. So like this I am drawing each silicon has how many valence electron? 4 valency. So this is a valence electron of each and every silicon. Observe carefully. If you can observe this diagram, then N-type as well as the P-type very easily you can understand. If you can understand this diagram, definitely P-type also unable to understand. Therefore, draw the diagram how all atoms are distributed inside of that silicon crystal. Okay. Now what happened here? This first electron of the silicon bonded covalently with the other silicon of the neighboring electron. Therefore, one covalent bond is going to become formed. Similarly, this is a second covalent bond. It is a third covalent bond. It is a fourth covalent bond. Like this, for each and every silicon. How many bonds are associated? 4 covalent bonds are associated. This is about bonding nature in the case of intrinsic silicon. Now what I am going to do? I am going to add phosphorus, which is a example for the pentavalent impurity. What is the meaning of pentavalent impurity? The elements which are having 5 valency electron, those elements are called as pentavalent element. Okay, so example for the pentavalent are phosphorus, arsenic, antimony, bismuth. This is an example for the pentavalent impurity. If you can observe the pentavalent impurity atom, how many valence electrons you can observe? 5 valence electron. Now this is about the intrinsic silicon, which contains all silicon atoms only, no other element is present. That is the nature of pure or intrinsic silicon. Our temperature T is equal to absolute temperature. Now what I am going to do? I am going to add one phosphorus atom. I am going to add one phosphorus atom into the pure silicon. Now observe the diagram carefully. Now I am adding one phosphorus impurity into the pure silicon. Already I am explained just now. Phosphorus has 5 valence electron. Therefore, it is the first electron of the phosphorus, second electron, third electron and fourth electron. But this phosphorus has 5 valency, so this is a fifth electron. Now we can observe the bonding nature after the doping. So out of the 5 valence electrons of the phosphorus, 4 electrons of the phosphorus bonded with the 4 electrons of adjacent silicon. So how many bonds are going to form here? 4 covalent bonds are formed. Okay, but this phosphorus atom has 1 electron extra. This phosphorus atom has 1 electron extra. This is a extra electron. This extra electron does not have any other electron to pair completely. Therefore, this phosphorus atom donates 1 electron to the one electron to the material. Therefore, the phosphorus nature is called as a donor nature. This donor electron is available just below the bottom of the conduction band. I will explain you using the energy band diagram in the upcoming session. Okay. Now this is our output at the temperature T is equal to 0 Kelvin. At this temperature, number of free electrons is equal to 1 and number of holes is equal to 0. This is temperature T is equal to 0 Kelvin. Now I am going to increase the temperature of this semiconductor above absolute temperature. As temperature is going to become increases gradually at a particular temperature, there exists breaking the covalent bond between the silicon and silicon or phosphorus and silicon. Whenever it happens, what happened here? One electron become free from the bond. This electron moving out of the bond. Now whenever electron moving out of the bond, the electron place migrate to the new location. This is called as a hole. Now this is called as a hole. Now we can observe the formation of one more electron free. Now we can calculate the total number of electrons in this material at a temperature more than absolute temperature. Already one electron is available because of donor type of phosphorus, and due to the increasing the temperature, one more electron is going to become formed. Therefore total electrons are 2 and number of holes is equal to 1. So holes is equal to 1. If we compare electron number and hole number, there we will observe majority number of free electrons and less number, that is called as minority number of holes. Therefore, if we can apply some amount of energy or voltage to this semiconductor, then maximum current is passing through the majority number of free electron. Therefore, this is called as n-type semiconductor. Okay. Now the same can be explained using the energy band diagram. This is about the formation of bonds inside of the n-type semiconductor, and it is about the energy band diagram of n-type semiconductor if temperature T is equal to 0. Okay, at this temperature this phosphorus atom has a extra electron which is called as a free electron. This free electron can create new energy level. This is called as donor energy level. This is called as a donor energy level. This level exists exactly just immediately below the bottom of the conduction band, and this is about the valency band and it is a conduction band, and it is a energy gap between the valency band and conduction band. If temperature increases above absolute temperature, then what happened here? Covalent bonds are going to become breakdown, which increasing the electron concentration, and consequently holes also created, and ultimately more electrons are there and less number of holes are there. This is about n-type semiconductor. Now coming to the second one is that is a p-type semiconductor. In a similar way I am explaining about the p-type semiconductor. So how can we define p-type semiconductor? When a small amount of travalent impurity atoms such as boron, aluminum, gallium or indium are added or doped into the pure semiconductor crystal, then the resultant material is called as p-type semiconductor because of addition of travalent impurity into the silicon or germanium. The following mechanism is going to takes place. Already we know that this is a travalent impurity. What do you mean of travalent impurity? These are having 3 valence electron. 3 valence electrons means it is a first electron of the boron, second electron of boron, it is a third electron of boron. So 3 electrons of the boron bonded covalently with the 3 electrons of neighboring silicon. So 3 bonds are completed here, but to complete the 4th bond for this silicon, here boron requires one more electron. Therefore this boron ready to accept one electron from the surrounding places. Therefore what happened here? Check the diagram. This electron shifted from this place to the newly located place. So here we observe the formation of hole. Here we can observe the formation of hole, and temperature is equal to T is equal to 0 Kelvin. At this 0 Kelvin temperature, there is no formation of free electron, only hole is created. So number of holes is equal to 1, number of electrons is equal to 0 at temperature T is equal to 0 Kelvin. Now due to the accepting type of boron, here new energy level is created just above the top of the valency band. This energy level is called as accepted energy level. This is because of accepted type of atoms, that is boron atom. Now as usual, if you can increase the temperature above absolute temperature, then between the atoms one or more number of covalent bonds are going to become breakdown. If at least one bond is going to become breakdown, it results formation of one electron free. One electron become free and one more hole is created. Therefore total number of holes is equal to 1 and number of electrons is equal to 1. If you can compare the hole number and electron number, there is a majority number of holes and minority number of electrons. Therefore if you can apply some amount of energy in the form of voltage or temperature, maximum current is or maximum conductivity passing through this material because of positively charged holes. Therefore this is called as p-type semiconductor, which contains majority number of holes and minority number of electrons. This is about n-type and p-type semiconductor.